as we watch the sun set slowly in the west, we can think about what this entire lesson package has been teaching you and what you've been learning. The idea that volcanoes in Hawaii are the result of a particular kind of interaction from the core of the Earth with a fixed hotspot was the scientific explanation in one of the previous lessons that you may have encountered. And of course, the Polynesian idea that Pele is the fire god who lives in the mountains and migrated down the archipelago as her sister Namakwa quenched the fires is a theme that we've looked at in an earlier lesson. In that comparison of ideas, we had presented the idea from the science side of thinking that there is a fixed hotspot and the plate of the Pacific Ocean floor has slid across the hotspot. This is a three-dimensional review of that idea in case you haven't seen it recently, or perhaps this is the first time. And you see the white arrows on the left side of the block are showing that the plate is sliding. We need to go back and think about plate tectonics. Plate is a normal English word. Tectonics, on the other hand, has its origins in other languages, and tectonics in this case means motion. So plate motion, again the white arrows indicating that a portion of the crust of the Earth, in this case the ocean floor, is in motion, and that needs to be examined in a further lesson consideration. There are several considerations about this motion. First of all, how much motion are we talking about? Is the skin, i.e. the crust of the Earth, sliding around, sloshing back and forth? No, it's indeed a very slow motion, perhaps not more than 2 to 3 inches per year that those white arrows represent. So it would take 5 years to slide a foot, and you can do the math and find out that it would take thousands, if not millions of years to slide the distance that is shown by the length of the island chain in this artist's rendition of the idea. Again, a fixed hot spot, and the plate slides over it, and blisters, if you want to think of it that way, are formed by this conduit of heat, the fixed hot spot. The idea that the Hawaiian Islands were formed that way seems to make a lot of sense, but what about the rest of the volcanoes? There are several hundred more in the world that are not perhaps associated with this kind of hotspot. So we need to return to some basic thinking and look at plate tectonics and how the plates themselves are shaped and where that data that they exist even comes from, so that we have more faith in our understanding of this concept of plate tectonics. Here from the National Oceanographic and Atmospheric Administration, NOAA, government agency, from their website is a picture of the globe, and they have adopted this as shown on screen from a textbook, and they have endorsed this in the sense of the red lines are boundaries in the solid crust of the Earth where there seems to be an unusual amount of some activity, be it earthquakes or volcanoes. You will notice perhaps that in the Pacific Ocean, where Hawaii is, there is little sign of a plate boundary. There is no red line. And that's because the Hawaiian Islands have formed by a different process. They are forming in the middle of a plate, and the plate is in fact moving as a unit over a fixed hotspot. But our focus at the moment is on these red boundaries and plates. And is it true that some volcanoes are actually on the boundaries of plates as opposed to the Hawaiian Islands, which were out in the middle of the Pacific Ocean plate? So to continue our quest, let's take that question. Why do we think there are boundaries as shown by these red lines. That's where we should begin our understanding of plate tectonics. This is a big question, and the question is large both in geography, in other words it's a global question, and it's a question large in time. We have to look through a long period of time to see what's happening on those plate boundaries. And so the Smithsonian has gathered together dozens of colleagues to work on this problem. The quantitative detection of earthquakes and their locations on the surface of the Earth really only began in about 1908. So it's been about 100 years that we know how to find where earthquakes really start or where they come from. And so the integration, the putting together, in other words, of 100 years data on where earthquakes occur is one place that this question and its answer can begin. The idea that the argument could be a little bit circular. Why do we think those boundaries are where they are? It's because it's located by the first early studies of where the earthquakes seem to be coming from, and then you turn the circle around and say, well, those must be important places in the crust of the Earth because there's a lot of earthquake energy being released at those places. So what the people at the Smithsonian have done is start with the supposition that the plate boundaries are real in the circular argument and put together a timeline of history. So if you take a few years, 10 years, 50 years, 100 years worth of earthquakes and plot them over that time period on a map, do they scatter in random all over the surface of the Earth, or are they in fact very localized in certain areas? And so that is what the computer program that the Smithsonian has put together allows even a user like you and me to do with a copy of the program, which will be included in this lesson. You can go in and dial up any time period that you want to see and have it plot on this map, and it's done very nicely even with music to make it interesting, the occurrence of earthquakes over a certain time period. If you see in the lower left of the picture on the screen is a yellow box, that's kind of like a calendar. Think of it as a time machine that you can start and stop the time over which you want to plot the location of earthquakes that have occurred throughout the whole world. Before we start playing the program or taking some snapshots of it, which we will do very shortly, some time slices, as it were, of the data, notice in the upper right corner there are some red dots. Those will show up as we start plotting data actually as white dots, but notice the size of the dot. That has to do with how much energy is being released at a given earthquake. A small dot is a small earthquake, a large dot is a larger earthquake, and the more formal idea of that in science speak is that that's called the magnitude of the earthquake. And again, it means simply how much energy was released. So we can watch for a couple things as we begin using this computer snapshot slice of time program. How big are the earthquakes? But maybe more importantly right at the moment is, where are they? Again, ask yourself, if they occurred all over the surface of the Earth with equal chance of happening, equal probability, the map would light up with, looking like someone had put a shotgun blast through it. But if in fact the plate boundaries are real, then we would expect that the earthquakes are in fact very much localized along plate boundaries. And again, coming back into the circle, it's chicken and egg. If the plate boundaries are real, then they must be places where earthquakes can occur. If the earthquakes that plot in this program are very local and not randomly located like a shotgun blast, then that is, closing the circle again, the idea that there is proof that there is some kind of very active junctions in the crust of the Earth, and those junctions, therefore, we call plate boundaries, if we can, in fact, prove that they exist by looking at the earthquake plotted patterns. With that background, let's in fact now take a first time slice. Let's ask the computer program to take 2 years worth of earthquakes and plot them over that time period on the same map. There you see the location of 2 years worth of data. Well, let's answer the question. Is it random, or is it pretty well concentrated? And we see definitely some lines of pretty solid dots in 2 or 3 places in the world. Let's zoom to the South Atlantic with Africa on the right and South America on the left and talk about this non-random distribution a little bit more. If you look down the western coast of South America, there's quite a few earthquakes. If you look between South America and Africa, there is a plate boundary suggested, and yes, sure enough, even in just a few years, the earthquakes in the ocean all seem to occur on that suspect boundary, not in the rest of the ocean. So in our first quick look, we seem to be coming to the place of understanding that it isn't a circular argument, or maybe it is, but at any rate, that the earthquakes do seem to localize on the red suspected plate boundaries. We can back out to look at the whole world again, and we see that there are other places, like in the middle of the picture, north of Africa, south of Europe, a large array of earthquakes that seem to be running right to left, and then over towards Europe and beyond Asia, out into the Pacific plate, all down the coast of China, Japan, and so forth. There is another huge array of earthquakes. So this idea that the earthquakes do seem to follow certain definite junctions in the crust of the earth does support the idea then that these red plate boundaries are very, very real. To be sure of our hypothesis, let's look at another time slice where we double the length of time from 2 years that we've just looked at to 4 years and see if the pattern holds up with a 4-year time slice. So that we can see what the next time period does. We've put those down in red, and we don't see many red places on the map that aren't superimposing on white spots. So if we doubled from 2 years to 4 years, we're seeing the same pattern, and the pattern is not random. It's very clearly decorating the suspected plate boundaries. Let's now go and add a longer. Let's increase our time slice now to 8 years, and again we will add the new data in red over the already existing map that we had produced with a computer. It's very clear that the plate boundaries are becoming almost covered now with data just in less than 10 years of putting down earthquake locations on a world map. Again, we have asked the program to plot on the map 20 years worth of data, and each increment of data comes down as red dots on top of the already existing material from our previous snapshot. If we zoom, we see a very convincing, extremely convincing pattern that almost 90% of the earthquakes are occurring in very regular patterns, and those patterns are in fact the plate boundaries that we started thinking about. In this close-up shot, notice particularly the heavy concentration on the west coast of South America. Tremendous amount of activity there, and yet you look at the rest of South America to the east, to the right, almost nothing. Another heavy concentration is right down the middle of the Atlantic Ocean, the so-called mid-Atlantic ridge, a ridge underneath the water which is known to exist from depth studies. So we know that this ridge is indeed also some kind of a plate boundary. What we have been doing is taking, as we've said, time slices or snapshots over various lengths of time of data and plotting it all on one map. I urge you strongly, with your teacher's help, to use the program that's supplied with this lesson to play this live It's very exciting, it's very fun to let this happen while you watch instead of just time slicing it. The yellow window clicks forward and shows you how much time has been added, and each time the window clicks, there's music enhancement, bing, 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 which is, each bink is a earthquake being plotted, and this data piles up. Let us look at two more slices in these snapshots, just to be sure that over a longer time period, in the name of good science, nothing else is changing. Here's a 30-year time slice, and it's still the same story. The map's getting perhaps cluttered with so many data points that it's not as clear as it was with shorter time period. Now we'll jump to a time slice of 40 years, and the pattern stays consistent. It melodramatically proves that these plate boundaries are absolutely and totally real phenomena. Let us return to the boundary of a plate and try to understand it a little bit better. For example, the Nazca plate and the South American plate. We saw the huge decoration of earthquakes along that coastline of South America between the Nazca plate and the South American plate. If we were to cut a slice between A and B and peel the Earth back and look down inside, what would we see along the AB profile? Let's do that. What is it that's actually causing the earthquakes along that coastline? The cartoon schematic that's up now shows you the Pacific Ocean floor and the South American continent, and the idea that there is closure in the plate tectonic motion, that the two plates are converging. Think of it, if you will, as almost a war of bulldozers crunching against each other right at the area called the trench. What is happening is the South American continent is causing the Pacific Ocean floor to downwarp, and the science speak word for that is subduction. And the idea that that black line decorated with the red asterisks is a plane of great friction, because South American continent and the Pacific Ocean floor are rubbing against each other along that downwarp area. That is called the Subduction Zone, named after another scientist, Benioff. And so this is often referred to as a Benioff zone in one of these closure or convergent plate boundaries. The earthquake energy, again, is being generated from the friction, and hence we saw all the earthquakes decorating the edge, the western edge of South America. Are all the plate boundaries similar? Are they all convergent, where they're crunching the plates against the edges of each other? To explore that, let's go to the mid-Atlantic ridge, which we saw was well decorated, and do the same thing, cut a profile along the line CD, and see what it looks like in cross-section at that area. By comparison, this cross-section is quite different than the convergence. As you can read here, this is a plate boundary of separation or divergence, where the two sides of the oceanic ridge are being forced apart or spreading, and a whole series of cracks and faults and disruptions of the ocean floor crust occur because hot magma all along for thousands of miles, the length of the ridge, seems to be coming to the surface from the mantle. And that magma intrudes its way up as it also cracks and distends the ocean floor into the blocky mid-oceanic ridges that are schematically shown. And each of the cracks or faults allows material to extrude to the surface, where in the cold ocean water, because we're in hundreds if not thousands of feet of ocean water, the red hot lava immediately quenches to a glass pillow-like lump of material, and so the ocean floor becomes decorated with extruded pillow lava piles of quenched pillows. Recall what we said, that this is divergent. that it is separating. You might think of it somewhat simplistically as the lava coming in and pushing the two pieces of ocean floor sideways. And if we use bulldozers to talk about convergence, maybe it's not quite scientifically right, but think about bulldozers pushing one to the left and one to the right. But the bulldozers are not real bulldozers. They're the arrival of the magma. The earthquakes that occur, as they occurred on the convergent plate with friction, here are perhaps a different type of earthquake. The shock waves are shaped differently as they arrive. They are gurgling of magma coming up these cracks, and the cracks are perhaps already produced for the most part, and the magma is just exploiting already existing cracks as it arrives at the surface. What we're saying is these earthquakes may not be quite as sharp as those caused in the convergent boundary, where friction is holding the plates together, and finally when they push hard enough, something cracks rather abruptly, rather suddenly, and the stored energy comes out in a much stronger earthquake. So the mid-oceanic ridges indeed concentrate earthquakes, but in general the earthquakes are of a different kind. The shock waves have different characteristics, and so the scientists can tell that that plate boundary being an oceanic ridge, is a different kind of mechanism than the frictionally controlled convergent plate boundary. Having looked at some of the mechanics of plate tectonics, let us return to this wonderful computer program put together by the Smithsonian and focus on the aspect of it that allows us to look at volcanoes now. Just as before, there's a time window, and there's a magnitude portion to the graph, and there's an event counter which tells us how many volcanic eruptions have happened during the slice of time that we may ask this computer program to display. So again, the map is fundamental, and we can dial up the computer program to give us a count of what volcanic eruptions have occurred during a given slice of time. This is a slice of time of 5 years showing what volcanoes have erupted. The color signifies what kind of violence or type of rock or magma was erupted. The gray triangles are volcanoes that are known to exist but haven't erupted in the time period that we have dialed up for our time slice. So we see a decoration, just as we did in the earthquakes, of some of the plate boundaries being very, very coincident with volcanic eruptions. It might be interesting to integrate more than just this 5-year slice of time. Again, the areas that we've looked at closest, the coast of South America, has had quite a few volcanoes located there historically, as well as quite a few colored dots, meaning recent eruptions in this 5-year time period. Interesting to note that the other place that we looked at, the mid-Atlantic ridge, doesn't show that many volcanic eruptions. But it may be like the old philosophical adage, if a tree falls in the North Woods and no one is there to see it, do we know it fell? And so since most of the mid-oceanic ridge volcanoes are submarine, and no one is there to see that happen, it may be somewhat more difficult, except by interpreting a seismic record, to know for sure that a volcanic eruption has occurred. You will recall that we saw that magma is oozing out along the dikes and cracks and faults and coming out as pillows, but that's not a violent eruption in many cases. It's a daily occurrence, but not violent. We can ask the computer program to take a 10-year slice of volcanic eruptions, and that has just come up on screen now. It's perhaps not as dramatic as was the earthquake increment in time, but again, how frequent are earthquakes and how frequent are volcanoes is part of what we're looking at here. There can be earthquakes that are dry of magma, frictionally controlled in convergent plate boundaries, as we've talked about, and that may help you understand why there have been many more earthquakes per time slice than there have been volcanoes. Again, the volcanoes that are not active in this particular 10-year time slice have been represented by the white-gray triangles. So we are seeing a decoration of all the volcanoes of the world over historic record keeping and where they are, and the color dots, by way of saying it again, are those that occurred in this 10-year time slice. Again, let us return to the computer program and ask for a 25-year compilation of data, which has just come up on the screen now. Again, the gray points are, you might say, historic, not active during this time period, but known to exist, and the color data points are those volcanoes that are on the continent, the showy ones, the ones that interact with society because they are in the way of mankind. Let's continue, and now we have taken a 35-year slice, and a pattern is developing, as we've already tried to point out, that along the coast of South America, a considerable number of volcanoes, the Andes mountain chain, is in fact almost all volcanic, if you've had that in some geography course. And while we do see some volcanoes decorating after 35 years the mid-Atlantic ridge from the top to the bottom of the world, they are not as common there as we've already explained. The idea that may be interesting is to look around the Pacific Ocean rim. This map happens to divide the Pacific in two pieces, and what we see is a very systematic decoration of North and South America, of Asia, Japan, and New Zealand, and that is often referred to as the circum-Pacific belt of fire, or ring of fire, meaning around the rim of the Pacific Ocean there's a tremendous number of volcanoes. Here is a close-up of the western Pacific ring of fire. In the upper right-hand corner, the two magenta triangles are on the Kamchatka Peninsula in Russia. You notice the volcanoes decorate down towards Kobe, Japan, and on down to the center of the picture of Pinatubo in the Philippines, and on around to the lower right of the picture, which is New Zealand. Let's look at a close-up of the other side of the Pacific Ring of Fire. Here we start at South America in the bottom center, and the very tip of land down there, if your Spanish is good, is, the name tells the game, Tierra del Fuego, the land of fire. We come up the coast of South America through the Andes Mountains. We come up through the 8 or 9 volcanoes in the United States that are volcanic and still active. Mount St. Helens, of course, going off in 1980 in our own. We come up the coast to Alaska and swing out to the left in the Aleutian Islands, all of them being volcanic mountains. It's probably worthwhile to take a few minutes and look at what we've just decided is happening on a map of the world that we've looked at in other lessons here, the Marie Tharp map. From actual sonar data, here's what the ocean ridges look like, and recall we've said that those are divergence or spreading boundaries in plate tectonics. By comparison, around the rim of the Pacific Ocean there is subduction or convergence of the plates as they collide with each other. Having reviewed these features and how they appear on this map, let's get a little bit more animated and go around the Pacific Ring of Fire as part of our review. The circum-Pacific Ring of Fire all around the Pacific Ocean comes from the idea that there are volcanoes here in South America. Tierra del Fuego is the land of fire, if your Spanish is good. As we come up, the Andes Mountains are all volcanic, come up through Mexico, through some of the western United States volcanoes like Mount Lawson, Mount Shasta, Mount Hood, on up the Alaskan and out through the Aleutians. All volcanoes would come to Kamchatka, the Russian peninsula, and we will visit that with some geothermal energy considerations, down through Japan, on around even down to North and South Island of New Zealand. And what is common, at least here in the Western Pacific, is this dark blue trench, and that's the indication that the ocean floor is indeed subducting and going down under the continental masses. And as it does so, it takes water and carbon dioxide down, maybe from shells and shales and clays, and those are released at depth and come back up, triggering volcanic activity, hence the ring of fire. In this review, recall that we looked at this schematic of how subduction works as a plate gets downwarped underneath a continent. We concentrated quite a bit on the South American coast, but this should be the same kind of cross-section almost anywhere around the rim of the Pacific Ocean. The geometry will change, but the ideas are still the same, that as downwarping occurs, there will be carried down the floor of the ocean and many of the things that are upon it, like shells and shales and muds and perhaps even trapped water. And as that becomes enfolded inside the earth, it's going down, the temperature is going up from friction and from increased temperature towards the core of the earth. We come to a condition where eventually on that subduction plane, the material is released as a gas, and that in turn fluxes the local rocks into melting, and since the melt is very light in weight, it rises to the surface to form a volcano. The Andes, as we've seen, are a chain of volcanoes. The rim of the Pacific, which is underlain by these kind of subduction zones, are a whole ring of fire of volcanoes that were produced in this manner. So we've spent now about 30 minutes learning a little bit about plate tectonics, and we got into this because we were trying to understand global volcanism. On the mid-oceanic ridges, which are plate boundaries of divergence, the magma is coming to the surface and oozing out on the ocean floor. Only seldom is it really directly observed. Here and there an island comes to the surface having been built up by the oozing material, but more typically the continental volcanoes we see are built up over convergence plate boundaries, where the two boundaries are in collision and material is taken down, and friction gives rise, along with core heat, to the melting of the rocks on the subduction zone. Hence the ring of fire around the Pacific Ocean. For review, this is yet a third map, but showing the same details that we've already talked about. The plate boundaries shown in black, the volcanicity shown in red, and the ring of fire pointed out one more time by way of review. And the third kind of volcanic activity that we have seen was the hotspot model by which the Hawaiian Islands occurred. A fixed rising of heat, a hotspot, a plume, while the plate tectonic motion slides a plate across it, and the heat stays in a fixed place, but the plate moving across allows volcanic mountains to form from the heat focused by the plume. This entire lesson, looking at the global reasons and locations for volcanoes, would have been impossible, or at least very much more difficult, without the program now showing on the screen, Earthquakes and Eruptions, which we have talked about, put together by the Smithsonian and many dozen colleagues who helped put together the computer program that plots slices of time for both earthquakes and volcanoes. This introductory presentation tape essentially is then a roadmap on how to use this and what it means when you do use it, so that you may interpret what you have the fun of doing now with the program that can be obtained from the website given both within the lesson and in the credit lines of this tape. Have fun. It's very interesting.